Welcome to the last lecture of week 5, and in this lecture we will see some more properties about tree width and tree decomposition that we defined in the last lecture. So, just for a recall, what was the tree decomposition of a graph G? Was a pair T and a set of bags x t associated with every node in T, with the property that for every vertex in V G there is a bag that contains it. Similarly, for each edge, right? And what we also saw that look at this tree T, and for any vertex V, look at the bags that all the bags that contains the vertex V. If you look at that, then they form a connected subtree. Okay. So, these are the three properties that we were looking for the tree width and tree decomposition. And up until now, we saw for several graph classes that we can construct a tree decomposition of small width. But first, let me today in our lecture, like I want to talk about is why do we care about tree width in parameterized algorithms? Okay. So, let me try to answer this question first. So, let us look at the first classical problem that we have studied, vertex cover. Okay. So, input was g comma k, parameter is k. Question: does G has a vertex cover of size at most k, right? Now, here is a way to deal with it. Okay. So, how can we deal with this algorithm problem is following. Okay. So, compute a factor 2 approximation in polytime in p time. Okay. If size of solution is strictly more than 2k, say no, or else what do you have? You have a set S who has size at most 2k, and what is this? This is an independent set. Now, right, this is our polytime. So, what we can do, we can make you make a path. Okay, suppose this is a vertex v 1 to v q, you make a path on t 1 t q and x I is just v I. Now, so this is a tree decomposition of v minus s. Okay. Now, add s to every bag. What have we got? So, we are able to show that the tree width of G is at most 2k, right? Now, so what are we able to say? So, in polytime, we are able to say either that this is a no instance, or able to compute a tree decomposition of G of width at most 2k. Okay. In fact, we can prove much better, much more. How? Look, remember when we do iterative compression. Okay. Now, in the iterative compression step, you have G I. So, either you are able to say that answer is no, or you have a k size solution. In G I plus 1, you have a vertex set S of size k plus 1, so that everything is independent set. So, in fact, in p time for G I plus 1, we can get tree decomposition of width at most k plus 1. Okay. So, all I am trying to tell you that this is why we care about, and it is possible to show, which we will see in the next week, is that what is the possible? given a tree decomposition of given, we can compute minimum vertex cover in time 2 to the power tree width to the power g and to the power big of 1. We will see this. But notice, so what are we able to do? We are able to show in polytime that either this is a yes or no instance, or we are able to come up with a tree decomposition of the graph, right? And we can exploit the tree decomposition through dynamic programming or compute some other kind of algorithms and get an FPT algorithm. So this is another route to design an FPT algorithm for vertex cover in running in time 2 to the power k plus 1 into polytime. Same story will hold for feedback vertex set, right? Same story can hold for feedback vertex set. So what will happen for the feedback vertex set? You will get a set S. Again, you can compute a factor 2 approximation, and this is a forest. So, and we know that the tree width of G minus S is at most 1, which implies tree width of G is at most mod S plus 1. So if you are able to bound S by 2k, you are able to come up with 2k plus 1, or if you apply this iterative compression idea, then you are able to show that tree width of G is at most k plus 1 or something. Okay. So, and again, if we had a dynamic programming algorithm for feedback vertex set parameterized by tree width, then we are done. And actually, in fact, such algorithms exist, and we will see some of these algorithms. Then we will start to use the when we start to do algorithmization of our tree decomposition. Okay. Okay. So, so these are the two properties which I want. So now let me tell you some other property. So this is like longest path or k path, whatever it is called. Okay. Input is gk, parameter is k. Question: does G has a path of length at least k? Okay. And for this, you must have seen in the last week a color coding algorithm. Now, let us see a magic using tree decomposition. So, what will we do? Okay. So, here is an algorithm. Compute DFS tree of G. So, I have computed a depth first search tree. Okay. So, what could happen? So, if suppose I started at root, maybe some root to leaf path is already length greater than k. Answer yes. But suppose it did not happen, then what can you say? Look at this graph. Okay. Look at this. Here is a root. Okay. And suppose we have L1, L2, L3, L4, L5, L6, so on and so forth. Now, what is the property of depth first search tree? Look at any non-tree edge. Where can the non-tree edge be? Every non-tree edge must be some root to ancestor, like this, like this. Okay. Now, you let L1, L2, LQ be the leaves of tree, this tree in order traversal. Fix something, does not matter. And now I am going to give you a path. So, now I am going to give a tree decomposition of this graph. What is my tree decomposition of graph? It has q vertices, T1, T2, TQ vertices. And what am I going to add? So, look at the Ti. So, XTi is going to be all vertices from R to leaf R. So, basically my first guy is going to be, this is my first bag. Second bag is going to be, this is my second bag. What is my third bag? Is going to be like this, so on and so forth. So, and now definitely every vertex is on the root to leaf path. So, every vertex is there. Every edge is on some root to leaf path, right. So, every edge is there. And now the only thing is, what about the vertices, right? Now, there try to show, this is an exercise using the properties of DFS, that the vertices, if you are going to, if the leaves are in pre or traversal, and then you fix this, every vertex will appear in the connected fashion. Okay. So, you should be able to prove this. So, what are we able to show? In poly time, we are either able to say this is an yes instance, or compute a tree decomposition, or compute a tree decomposition of width, in fact, width at most k. Okay. And now, there is a dynamic programming algorithm. There is a dynamic programming algorithm on graphs of bounded tree width. And that will help us get the desired FPT algorithm. Okay. So, let me give a last example, and this is called max leaf spanning tree. Okay, or rather, okay, yeah, max leaf spanning. Input is G comma K. Question. Okay. And the question is, does G has a spanning tree T with at least k leaves? Okay. Okay. So, what will we do? Okay. So, algorithm does follow. Compute a BFS tree, say T. So, I have computed a BFS tree. any layer Li, okay, if any layer Li has more than k vertices, suppose there is a layer which has more than k vertices or greater. So, now look at, okay. So, now, so I have, right, here is our, right, with more than k vertices. Now, look at this, this is suppose layer Li. Now, because graph G is connected, like you can always either you can always extend this partial tree to a spanning tree, okay, that has at least k leaves. Okay. So, if any layer has more than k leaves, then you know that you have a tree, subtree with at least k leaves. Then I am claiming if graph is connected, then you can extend that subtree to a spanning tree of my whole graph without sacrificing the number of leaves. It is a good exercise, please try. Okay. But what does this imply then? Okay. So, this implies that either we are able to find a spanning tree with at least k leaves, or all the layers of BFS tree has at most k vertices. Okay. Okay. So, suppose L0, L1, L2, so on and so forth. Now, notice one thing, what is the property of BFS tree? The property of BFS tree is that a node here can only have an edge here, it cannot jump here, there is no such jumping. So, in fact, if you notice, each layer Li separates vertices in L0 to Li minus 1 from vertices appearing in Li plus 1 to say Lq, some q. Now, we can get a decomposition. So, suppose there are q layers, then we can again get a decomposition. Here is our path with T1, T2, Tq, and each Ti is nothing but what? So, x of Ti is nothing but say Li union Li plus 1, right. So, this and you can show again, you can show that this forms a this is very easy to show that this forms a valid tree decomposition, and in fact, what is the tree width of this graph? Then this implies is at most 2k minus 1. Okay. Yeah. So, and again, if we had a dynamic programming algorithm and graphs are bounded tree width, then we can exploit the structure that we have got on the input graph to design an FPT algorithm. Okay. So, this approach is what is called win-win approach. Why? So, either we are able to answer the problem, or right, either we are able to answer the problem, or we find our tree decomposition of G as a function of input parameter. Okay. And then use this structure to do DP or other algorithmic technique to solve our problem. I hope this set of 4 or 5 examples would have explained you the importance of tree width or tree decomposition in construction or in the designing of fixed parameter tractable algorithms. Okay. Now, I will take a small detour and spend some time telling you some properties . Okay. let me tell you some structural properties like of tree decomposition. Okay. Okay. So let me tell you some interesting structural properties. So let me prove some lemmas for you. Okay. Okay. So from now onwards, you have a fixed graph G, and we are talking about a fixed tree decomposition xt. Okay. Let T1, T2 be an edge of T. Okay. And let T1 and T2 be the components of T that contains T1 and T2 respectively. Okay. Then xt1 intersection xt2 separates u1, which is by definition, what is u1? Union T in vertex set of T1, okay, xt, and ut is like union T in vertex set of T2 xt. Okay. Okay. In G. So let me draw picture wise what I mean by this. So suppose here's my tree. Okay. So suppose this is my tree T, and suppose this is the edge we are talking about. So this is like T1 and this is T2. Okay. Now what is the meaning of this? It tells us that look at a graph where what is U1? U1 is basically union of vertices in the bags here, and what is U2 is union of vertices in the bags this. And what it tells us that like if you delete xt1 intersection xt2, so this is some vertex. Now there is no edge. Suppose this is u1 minus, let's call this z, and so this is my z, and this is u2 minus. There is no edge from u1 minus z to u2 minus z. Okay. Okay. This is all that it says. Basically, it tells us that look, it is indeed, if you look at the edge and look at the intersection of vertexes, then it indeed forms a separation. It separates left part of my graph from the right portion of the graph. Okay. Okay. Now say, why is this true? The proof is very simple. It's like one line. Why? Hey, so let's cut this, copy. Okay. Now, suppose there is some vertex here. Suppose there is some vertex here, A, and there is a vertex B, and there is an edge here. Okay. Now, what is the T2 property implies? Property T2 implies there exists a bag containing both A and B. So where can that bag be? If that is a bag, so see, B is in some bag in this side, A is here. So, if that bag, if suppose that bag is somewhere here, okay, that bag is somewhere here, let us say, suppose that bag is somewhere here. What happens? So, if this is a bag that contains both, suppose it contains A and B, then what do we mean? No, there is a bag here that contains A and there is a bag on the other side that contains A. It means, look at the unique path from here to here, all these guys will contain A, otherwise the bags containing A cannot be connected. Okay. Or similarly, this bag could have been, if this bag is say here and suppose A and B is here, then we would have said, well, if that is the case, then look at the path, which is this, look at this AB path, right. Now, B is also here and B is also in this bag, then B is also part of every bag, and in particular B is part of the intersection xt1 intersection xt2. Okay. So, this immediately implies there is a bag containing both A and B, and from here we can infer the desired separation property. Okay. Now, notice this is how we actually were trying to construct our tree decomposition when we were discussing, which we will see later when we were constructing, but it does satisfy the property we wanted, that if I look at the set of vertices which is part of, like, look at edge and whatever I have associated, if I delete this, then it does disconnect the graph which is stored below me from the graph which is stored outside. Okay. So, in some sense, when I look at this T1 and T2, then it basically tells us what is the kind of graph. Okay. So, this is how the world, if I look at the graph case, then this is how it looks like. Okay. So, this xt1 intersection xt2 separates some vertices from here. So, this is like, so this was the graph below this T1, then this is a set of vertices which is kind of guarding or is just separating from the below graph from somewhere outside. So, this is the kind of separation property we were anyway looking when we were trying to construct those decomposition, and indeed this decomposition has that property. Okay. So, let me prove another property to you which is nice. Given a set W, subset of Vg, there is either a T in T such that there is either T in T such that W is subset of Xt, or there are vertices W1 and W2 in W and an edge T1, T2 in T, T2 in T, such that W1 and W2 lie outside the set xt1 intersection xt2 and are separated by it in G. Okay. So, what is this tells us? So, let us try to understand what is this tells us. It tells us, okay, so suppose this is my tree, decomposition tree, okay, and now you gave me a set W. So, either I will be able to find you one node and a meeting where W is completely contained inside this, or I will find you two vertex, or I will find you two vertex W1, W2, okay, and an edge, right? And what is the property? That first of all, W comma W2 is not an element of xt1 intersection xt2. That's the first thing. And but we know that if they do not belong to, and if you remove this, then there is no path from W1 to W2, right? So this is just a, so what does it mean? So basically it tells us that what this lemma tells us, that if you give me a set W, either I can find a way to separate it, or this W belongs to the one bag. Okay. So now let's prove this. Okay. This is not, proof is not very hard. Okay. Okay. So proof. Suppose there is no W1, W2 and T2 and T2 that has separation property. Okay. So suppose we can't separate W, right, by an edge. Like every edge has a property that, like, yeah. So, okay. So now given this, now we need to, so suppose this does not happen, that you are not able to separate, like you are not able to separate, like you delete an edge and W1 is W2 is not there, then we need to show that there is a bag that contains whole of W. Now that's a, so this is a trick which I would like to teach you. This is called orientation trick. Okay. Now we have this tree. Okay. So I just pick up an edge. Okay. I pick up this edge. Okay. And suppose this edge is T1 and T2. Okay. And now I ask myself whether W is a subset of, say, U2. Remember what was U2? E2 was the union of all the vertices here, and U was the union of all the vertices here. Okay, baby. Okay. So this is my okay. This is my U1 and this is my U2. Okay. So I ask myself, look, whether W is completely contained inside U2, right? If that is the case, because look, it is not possible that some vertex of W is here and some vertex of W is there, and that guy does not occur in T1, T2. This cannot happen, because otherwise then we would have found the separation and we are done. So what is the property? Then the property that, look at any edge, W is either entirely contained inside here, or W will be entirely contained inside this. Right? But it is not possible that there is some vertex of W here and some vertex of W here, and these two guys do not occur here. Okay? This cannot happen. So either W is, whether W is subset of U2, if W is belong to a subset of U2, you take this edge and you orient it towards T2. Okay? Orient the edge T1, T2 to T1 directed T2. If W is subset of U1, then what we would have done? We would have just oriented then T2, T1, like T1, T2 to T2, T1. This is how you orient. So basically what I'm saying, I'm looking at an edge, I say which side contains W completely. Whichever side it contains completely, I point my arrow towards that side of my tree. Okay. So, this is what we do the whole orientation. Now, and this is fine. Look, and for every arc you will be able to find such an orientation. Okay. So, this is perfectly fine. And now, what will we do? Let P be a maximal path in T, like P be a maximal, directed maximal path in T. So, suppose this is a maximum directed path. Okay. This is in T, and suppose okay, and suppose this is my last vertex. Okay, this is okay. Now this is okay. Now if this is a directed maximal path, what is the meaning of this? All the arc which is going are like this. All the arc which is going are outwards from here. Right? And look at this T. Okay. I claim W is subset of this bag. Okay. Let us see why. Let W be element of W. This implies there exists a bag, say x t prime, say some t prime, such that x t prime contains W, little w. Okay, okay, fine. So, if t prime equal to t, no issue, because W is also there. Otherwise, look at a path from t prime to t. Look at a path from t prime to t in t, not in the oriented. So, now let us look at this path. Okay, look at this path. Now, okay, so there is a path from t prime to t, right. Now, look at the last edge. Look at the last edge. Okay, look at this edge. Look at this edge. Okay. What is an orientation of this edge, right? So the orientation of this edge is towards t, right? Orientation of this edge is towards t. Why? Because why the orientation of this edge is towards t? Because if the t does not have any T does not have, and what you call, T is like a sink, T is not a source, right? Because, yeah, so T, like, what is the property of T? T is not a source, like, it does not have any outgoing edge, it only has incoming edge, okay? Okay. So, because of this, what is it? So, what is this orientation implies? Orientation implies that W is contained inside. If you delete this edge and look at the world here, okay, there must be, right, there must be sorry, okay, okay, oh, sorry, I lost it. So, basically what I am saying is that delete this arc and look at the objects here, look at the, so this is like some, okay, let me draw better. So, suppose this is a tree after I delete this as. Now, what is the meaning that of this edge? It means W is contained inside the vertices of the union of these bags. Okay, but then what does it imply? This implies that there will be some t double prime here, some t double prime where w is contained inside x t double prime. Then look at this, w is here, right, which implies what? That w belongs to every vertex on every bag on this path, and in particular this implies w belongs to xt. Okay, so we have shown that so we have shown that w is a subset of xt. So this concludes the lemma. Okay, and now here's my exercise. So my exercise is show that any clique of G is contained in some bag. Okay. Okay. So so now let me prove one last property about three-state composition. So these two properties which I talked about is kind of separation. So if you give him any big set, tree decomposition has a separator which separates it. Okay, this is what it is trying to tell. Okay, so now let me tell you last property. Okay, the notion of simple tree decomposition. Okay. So what is the notion of simple tree decomposition? So tree decomposition t comma xt of G is called simple if the following if there doesn't exist some t1 t2 such that xt1 is a subset of xt2. Okay, meaning what it tells us, a simple tree decomposition is the one where no bag is contained inside the other bag. This is the only property of simple tree decomposition. Okay, so first of all, okay, so this is the okay. Now notice that why does, so there are several questions. The question number is, why does say simple tree decomposition exist? Oh, that this is, so what you can do, this is very simple. We can start with any tree decomposition and make it simple. Okay, how? Look, okay. Now, first make sure that, now notice that suppose there is some, say here is like some t and some t prime where xt is say suppose xt prime, then actually there exists an edge here, okay, t double prime, such that xt is contained inside xt double prime. Why? Because of the connectivity property, in fact xt will be part of every bag on this path, right? So if this is non-simple path, then there exists an edge which is non-simple. Okay, and how can we get rid of non-simple edges? Is very simple. So what you do is that look at this t and t prime. Okay, you look at this t and t prime. So in this tree decomposition, suppose I found I have a t and I have a t double prime, and suppose xt is contained inside x double prime, then suppose here it is, and suppose this has some children, then what you do, the transformation is that you take t double prime and all these guys you make them directly adjacent to t double prime, and you forget, like you throw away t. So you make some changes. So suppose this is t and it has children say T1, T2, T3, then you forget T and you make T1, T2, T3 directly T double prime, and that's it. And you can still show that this forms, this is a very valid tree decomposition, because no property will be violated, because a subset is contained inside this. So, edge property will hold, vertex property will hold, and the connectivity property will also hold. Okay. So, you can go bottom up. You start with a non-simple tree decomposition and you bottom up, you apply this transformation and convert a tree decomposition to a simple tree decomposition. So, this is another simple fact that is important to know. Now, it has some very beautiful properties. So, this is some exercise which I want you to think about it, and if you are not able to do, we will do. Okay. So, because of the simple tree decomposition, okay, first show that if tree width of G is at most k, then it has a vertex of degree at most k plus 1. Hint: use simple tree decomposition. Second, there exists a tree decomposition of G of width at most k, where vertex set number of vertices in T is less than number of vertices, less than at most. Again, hint: use simple tree decomposition. 3, so that if in fact say k, so that if tree width of G is at most k, then number of edges in the graph is at most k times n. Use 1. Okay. So, this is the 3 exercises which I would like you to try out, and if you do not succeed, I will do it, but with this I will conclude this week lecture about tree decomposition, and next week we will see some algorithmic properties of tree decomposition. For example, how to compute tree decomposition, how to design dynamic programming algorithm on tree decomposition, and as a final touch we will also see how to get sub-exponential time algorithms on very special classes of graphs such as planar graphs, epics minor free graphs, and some such things using tree decomposition and some simple properties of planar graphs. Okay. Okay. With this, let me conclude my today's lecture.